A battery bank the size of a suitcase is quietly running a fridge, 3 lights, and a well pump through a blackout. The neighbors have no power. This house does. Total build cost lands in the same range as 1 month of a bad power bill. Nowhere near what a whole home standby generator system costs installed. The cheapest critical component in this entire build, a transfer switch or interlock kit, is the only reason any of this is legal or survivable. That switch has a rating on it that matters more than the size of your battery bank. Get that one number wrong, and it doesn't matter how many kilowatt hours you bought. By the end of this video, you'll understand exactly what a transfer switch actually does, why bigger battery doesn't mean safer house, and how to size the switch, the wire, and the battery together as one system. You buy a battery backup system, and you assume it means your house is backed up. It doesn't. It means whatever the transfer switch and its subpanel decide to hand off is backed up, nothing more. People buy a big battery, wire it into a random circuit, and discover on the first real outage that half their loads never got power at all, while the other half tripped the inverter offline in the first 10 minutes. The commercial whole home backup pitch hides the same assumption in reverse. It's sized and priced for the panel's theoretical maximum draw when you were only ever going to run the fridge, the router, and a few lights. A manual transfer switch is legally allowed to rely on you, the human, to only turn on what the inverter can handle at once. Skip that judgment call, overload the inverter, and it shuts itself down mid-outage. None of this is a battery problem. It's a switch and sizing problem, and almost nobody frames it that way. Start at the utility service entrance, where grid power enters the house, then the main panel, which feeds every circuit under normal conditions. Between the main panel and your backup load sits the transfer switch, the one component whose entire job is deciding which source, utility or battery, touches the wires downstream, and making sure it's never both at once. Downstream of that switch is a backup subpanel, holding only the circuits you've chosen to protect: fridge, well pump, a few lights. Feeding that subpanel is the inverter, converting your battery's direct current, or DC, into the alternating current, or AC, your appliances expect. Behind the inverter sits the battery bank, the energy reservoir the whole system draws down during an outage. One-sentence version: power normally flows straight through from the grid, but the moment utility power drops, the transfer switch disconnects that path completely before it reconnects the backup subpanel to the battery's inverter. One source, one direction, one connection at a time. Everything in this build lives or dies on one idea. 2 power sources are never allowed to touch the same wire at the same moment. Engineers call the mechanism that enforces this break before make. The switch fully breaks the old connection before it ever makes the new one. Picture a single-lane bridge with a gate on each end. Cars can cross toward town or cars can cross away from town, but the gates are built so both directions can never be open at once. Open both gates together, and cars from opposite directions meet in the middle at full speed. That's exactly what happens electrically if a transfer switch fails or is bypassed, while the grid comes back online mid-outage. 2 unsynchronized power sources collide on the same wire. Hold on to that single-lane bridge picture. It's the reason every rule in the next 2 sections exists. The transfer switch itself comes in 2 flavors. A manual switch means you physically choose which loads run, and you carry the responsibility of not turning on more than the inverter can handle at once. An automatic switch senses grid loss and switches on its own, but it must either be sized for the full connected load or paired with a load management system that actively sheds circuits to stay under a safe ceiling. The spec that matters when buying either one: it must be explicitly rated for the type of power it's switching, DC-rated hardware for DC components, AC-rated hardware for AC components, and its voltage and amperage rating must exceed the maximum your system can ever produce. The inverter converts your battery's DC into household AC, and the one spec that matters is its continuous power rating, not the number on the box in bold, the number in the fine print. Inverters can briefly exceed that rating for a few seconds to handle a motor starting up, sometimes more than double the running wattage, but that's a surge allowance, not a sizing number. A sensible margin is to pick an inverter rated meaningfully above your actual connected load, not exactly at it, including headroom for motor starting surges. The battery bank comes down to 2 practical families: lead-acid chemistries, flooded, gelled, or sealed AGM, the cheaper, well-understood default, and lithium iron phosphate, or LiFePO4, which costs more upfront but holds more usable capacity per pound and tolerates deeper discharges. Neither is a brand decision, it's a usable energy per dollar decision. Let's size this for real. In 3 scenarios: small, typical, and heavy use. First, the hard ceiling. In backup mode, your total simultaneous load can never exceed the inverter's continuous power rating. A standard 120-volt backup inverter might carry a continuous rating around 3,600 watts. Run the fridge, a couple of lights, and the router at once, and you're nowhere near that ceiling. That's your small scenario. Add a well pump and a window air conditioner cycling at the same moment, and a typical household can walk right up to that number. Try to run all of it plus space heaters, and you've built the heavy use case that trips the inverter into a protective shutdown, not because the battery ran dry, but because the wattage exceeded the ceiling. Second, runtime. And this is where most people guess wrong. Say your chosen backup loads draw 7.35 kilowatt-hours or kilowatt-hour over a day. You don't get to draw that straight from the battery. You lose energy at the inverter, roughly 94% efficient, and in the wiring, roughly 98% efficient. Divide instead of multiply. 7.35 kilowatt-hours divided by 0.98 times 0.94. Approximately 7.98 kilowatt-hours actually required from the battery bank. Those two small percentage losses compound. You need roughly 8 to 9% more battery capacity than your appliances actually consume. Convert that to amp-hours, or Ah, on a 48-volt bank. 7.98 kilowatt-hours times 1,000 divided by 48 volts, approximately 166.2 Ah of battery has to be discharged. But you never run a battery to zero. Depth of discharge, or DOD, limits are typically 80% for lead-acid batteries, which means you need 1.25 times the raw number as your usable bank size. 166.2 Ah times 1.25, approximately already 107.8 Ah minimum. That's your typical scenario. Size smaller, and you're the small scenario, running out mid-outage, oversize the bank without checking the inverter's continuous rating, and you've bought heavy-use battery capacity feeding through a small scenario inverter, which brings us back to the ceiling from a moment ago. Third, the wire and breaker between the inverter and the transfer switch. Continuous loads require both the wire and the breaker to be rated at 125% of that continuous current, so a steady 15.8 amp draw needs wiring and a breaker rated for at least 19.75 amps, which is why that circuit typically lands on 12-gauge wire and a 20 amp breaker. Undersize that wire, and you've built a heat source inside your wall, no matter how correctly you size the battery. Phase 1. Design and permit before a single wire is touched. A licensed electrician runs the load calculation and pulls the permit. Homeowners are generally not permitted to self-install a battery-based energy storage system. Phase 2. Mount the backup subpanel and the transfer switch, and decide the grounding architecture before any wire runs. Pick this wrong, and you either create a shock hazard or a code violation that fails inspection outright. Phase 3. Install the battery bank and inverter, and wire the DC side first, fully isolated from any AC connection. Never connect the inverter's AC output to the subpanel before the battery and DC wiring are complete and verified. Phase 4. Run the AC tie-in from the inverter to the transfer switch and subpanel, sized per the 125% continuous current rule, respecting the busbar rule so the combined rating never exceeds the busbar's safe limit. Phase 5. Install every required sign, the permanent placard at the main service equipment, identifying the standby source and its location, and a second one at any remote grounding point. Phase 6. Rough in inspection, with every wire and box interior fully visible before anything is covered, followed by final inspection once the system is complete and the breaker directory is filled out. Only after a passing final inspection is this system legally and safely live. Failure 1. The silent overload. Symptom: the inverter shuts down mid-outage for no obvious reason. Actual cause: the simultaneous connected load crept above the inverter's continuous rating. Failure 2. The backfeed ghost. Symptom: utility line workers or neighbors report shocks or strange readings on lines that should be dead. Actual cause: a bypassed or missing transfer switch lets backup power flow backward through the service entrance and into the neighborhood step-down transformer, multiplying household voltage back up to thousands of volts. Failure 3. The runtime mirage. Symptom: the battery reads full on the display and still dies hours earlier than expected. Actual cause: the original sizing used raw battery capacity instead of compounding the real losses. This build is governed in the United States by the National Electrical Code, or NEC, primarily Article 702 for optional standby systems, and Article 705 for sources that interconnect with the grid. Every transfer switch must be listed for its use and must use break-before-make switching. A licensed electrician is required to install a battery-based energy storage system and to pull the permit. 2 inspections, rough-in and final, are standard, and the required standby source signage at your main service equipment is not optional paperwork. If you're building outside the United States, the same core principles still apply: break-before-make isolation, a qualified installer, proper signage, but confirm your own country's wiring code and local authority requirements. This video is educational and not professional electrical, plumbing, or structural advice. Codes vary by location and change over time. Mains voltage can kill, and stored water and stored energy can both destroy property. Have your plan checked by a licensed professional and your local code office before you build. Add up the transfer switch, the subpanel, the wire, the breakers, the inverter, and the battery bank, and you land well under what a fully installed whole home standby generator system costs. You're buying a specific, correctly sized set of circuits that keep running when everything else in the neighborhood goes dark, and the same critical load subpanel you just built is the exact foundation the next system. A solar charging array will plug straight into. Educational only. Verify against your local code. Build it once. Understand it forever. Subscribe if you want the rest of your homestead explained the same way.